Look a little bit into the implementation of this, and there are basically kind of two main pieces, or two or three depending on how you count. We've been looking at ways of turning uniform 0-1 random numbers into random variates having a particular distribution. So far we've looked at the inverse transform method and something called the composition method, where we use what's called a mixture of probability distributions. There's a third way, which is what's called the acceptance rejection method, which is basically what you do when neither one of those completely works. And actually, typically for certain random variables, it can be a little problematic to apply these because the conditions may not be met. So for example, for the inverse transform method, you need to be able to write down the CDF and also invert it analytically. There are ways of inverting them approximately using polynomials, ratios of polynomials, and things like that. We won't get into that. So it turns out that for difficult random variables, then this acceptance rejection method that we'll talk about, not today, but some other time. But first, there is a little bit of that issue that I mentioned the last time, which is, do you really believe these? Now, if you're sort of knee-deep or neck-deep in the math of it, then you sort of believe the math. But on the face of it, there are things like just even our basic triangle, the triangle distribution that we had, the method required taking the square root of a uniform 0-1 random number and claiming that that produced a random variable whose PDF would look like a triangle, that is, have a straight line to it. And as at least some of you didn't believe that, which is fine. There's no reason why you should. So what would make one believe? Well, if you generate a bunch and then kind of look at the histogram of it, and if it kind of looks linear, then that might convince you. That plus the fact that it's mathematically valid. So in order to do that, we need to implement them. The implementation that is just the framework that SimKit uses is an interface, an abstract base class, which is optional, and this thing called a random variate factory, which we've been using and we'll kind of look at a little bit at some point today. So here's, at least in the upper two, are the interface and the abstract base class. So the main thing is the interface, the random variate interface. We've been using that as the type of our random variates. So right from the beginning, whenever we needed a random, something to generate randomly, from the inter-arrival times of the arrival process to the service times to whatever else was going on, we declared that as a random variate. And the random variate is an interface, which, as you all know, cannot be instantiated. So if I have something which is only an interface, how do I instantiate it? There are a number of different ways. The only thing that you can instantiate is a concrete class, and in this case, if I declare a variable to be a random variate, then the only concrete object I can put in that variable is an object which implements that random variate interface. On the other hand, so why bother with this? Part of the reason is that we can create our components before knowing what the specific random variable that we're going to be putting in there is. In other words, if we're working on modeling a particular situation, and we're still working on figuring out what the particular random variable to use for a piece is, that isn't a showstopper in terms of developing the model. We can simply declare it to be a random variate. We can use some kind of placeholder to even test it out. And then when we finally have figured out exactly what it is, then we can use that instead without having to edit our component. In other words, we can verify our component without knowing the specifics about it. That's the reason why there's this extra machinery. Now, the principle of having abstract base classes is that if there's common things that every instance is going to do, then it's convenient to put it in an abstract base class. It's not, in this case, it's not super necessary, but in this case, there's something called random variate base, which, and all it does is it provides a random number variable with a setter and a getter. So the parameters for a random variable, every random variable requires a stream of uniform 0 or 1 random numbers. So how do we do that? Well, we have an instance of a random number, and it has a setter and getter, so we have complete flexibility in terms of which one we decide to use. Should we decide to use it? We haven't really taken a look at that. Why? Because when you get your random variables through the random variate factory, then what's happening under the hood is that there is a single random number instance, which is the default random number of the random number factory, which in this case is a Mersenne twister, which is the good one that we decide to use. And so here are 3 concrete classes, and these are the right triangle variate is one that we did. We did the triangle composition variate. That's one that we did to illustrate composition, and then we also looked at exponential, and then there were a couple of others that we've done. So what are the pieces? Well, first, we do require a 0 argument constructor. Again, that goes back to sort of meeting the Java Beans specifications. We require a random number parameter with a setter and a getter, or we can use the random variate base, which provides one. Now, in terms of what we have to write, for the parameters, we have to write 2 generic methods. One is called get parameters, and that returns actually an array of object. We can kind of see that here. That is right here. So get parameters returns an array of objects because different random numbers have different types of parameters that they might have. And so we need to be as generic as possible as that. As it turns out, Java generics don't really kind of do the trick for that. The second is that we have a setter, and the setter for the generic setter, again, it's a varargs. Internally, of course, that comes in as an array of objects, and so the things we need to do, we need to, first of all, check for the right number of parameters. So as we've seen, for example, in our right triangle variate, it had 1 parameter. Our exponential had 1. That triangle that we did, which was a full-up triangle, it had 3 arguments. And so the first thing we do is we check for the right number of parameters. So if I have like one of those full triangle composition things that we did, and I don't give it 3 parameters, then what is it supposed to do? So the first thing is say, did you give me the right number of parameters? And then because these are, the method is just objects, we need to check each parameter for the correct type. And then once we pass all that, then we call the setter, because each parameter that we have is going to be a regular parameter with a setter and a getter. as I said, the abstract base class, all it does is it just implements a little piece of it. It has the random number parameter with the setter and the getter, and that's what is it called by? Okay, so the concrete class. Okay, so we can either implement the random variate interface or extend random variate base. We need to add any parameters required for the distribution. So for example, for a right triangle, there was that parameter we called B, which was the maximum value. And so we would need to implement that as a parameter as we've been doing, a private instance variable with a setter and a getter. We usually want to override toString, again, just to make sure that we're passing the right parameters, and so that's the key is the generate method. So whatever method we're using to generate that random variable, that's where we implement in the generate method. And we've used the generate method a few times. And what the benefit of that is that if I have a random variate and I want to get the next value, I just call generate, and I don't have to worry about what kind it is. Now, in terms of the name, the convention is that if I have the name and then say blah-de-blah variate, that's optional, but generally desirable just because it signals that that's what this thing is. Now, the random variate factory that we've been using, and again, this is a common pattern when you're trying to get instances of things where all you know about it is that it implements a particular interface. You can't instantiate the interface, but the factory kind of just does what you would do in a factory. If I want to get something for the factory, I place an order. So when we have used the getInstance method in the random variate factory, a static method, it goes through and tries to figure out, okay, what is it that they're asking for? So I give it the name, it's overloaded, but the main use is the get instance. We have a string and then a var arg of objects. And those objects will be what our parameters are. And it's a var args because each random variate would have a different number. Again, we've already seen that. We've seen some with one argument, like exponential or the right triangle. We're not here, but we've seen some, actually, yeah, here remember that wedge variate that we did? That had two arguments. The triangle had 3. So the name, now the name needs to match a class which either matches that name or matches that name with the word variate after it. So the random variate factory kind of looks for something with that name, and then if it can't find it, it looks for something with that name in the variate and stuff like that. So say for exponential, we'd pass it 1. We've used uniform, we would pass it 2, etc. Now, the built-in, if we just use the getInstance method out of the box, it looks in the SymKit jar file for the classes. And it's useful, though, to have the ability to use the random variate factory in the same way for user-defined classes. And there are a number of ways of doing that, but the most straightforward, is to simply say, call add search package and give it a string, and the string is the package telling the random variate factory, look in this package for stuff. So for example, and we'll see in a moment, if we add the search package move 3302.random, it says, look here for random variate stuff. We could also use the fully qualified name. That works even not doing that. But fully qualified name is a pain.
For those you would be putting in like the right triangle, exponential, or triangle.
Exactly, yeah. So let's, okay, first of all, and this is in the Moves 3302 random package. Let's take a look at, okay, we did the right triangle. So here's the right triangle. Again, in this case, I've extended random variate base and implement, this is just the implements is, I don't need that, but that's just to be absolutely clear about exactly what it's doing. It has one parameter. This was the one we were calling B, you can say the max value. So here's where, so for example, so in the set parameters, and this is typically what you need to do because the user now, because the user could pass all kinds of stuff. What could go wrong? Well, what could go wrong is it could not pass you any parameters, or it could pass you, supposing I'm trying to use this and I pass it 2 parameters. Well, there's a mismatch then between what the user thinks this is going to do and what it's actually going to do. So in that case, I'm going to throw an illegal argument exception if you don't give me exactly 1 parameter. Now that's sort of optional. I could be more loose with that and say you need to give me at least 1, and if you give me more than 1, I'm going to ignore all but the first one. That's a judgment call. So how, in this particular case, again, my reasoning is that if I want to use this random variable and I give it more than 1 parameter, then that means that there's some kind of something that's off here. So I'm not going to let you go by. Now, just because I have 1 parameter, because the argument is an object, it could be anything. I could pass it a string. I could pass it another random variable or something. So that needs to be an instance of number. And here typically we're going to pass doubles, but I could pass a float. I could pass an integer, and all of that would be fine. If I want an exponential with or if I want one of these right triangles with a parameter of 3 and I pass it just an integer of 3, I don't want to have to, I don't want to say, no, I'm not going to do that. So remember, the object wrappers for numerics is a number is the abstract base class for all numeric things. So if you give me a number, then I'm always going to be able to pull a double value out of it regardless. So if it's a number, then I can call the setter, casting it to a number, and I can safely cast it because I protected it with this. So that's how you do the setter. The getter is, the get parameters, that's typically fairly straightforward. Again, setter and a getter for this. And then the toString, typically you want to override the toString just when you're testing it out. The main thing back here is the generate. So here's the generate method. If you remember, what was the equation? It was b times the square root of u. Now, RNG is the random number. Draw is going to draw a uniform square root. It's going to take the square root and multiply by the max value. Okay, so there's the implementation of that. And here's how we can use that. Let's see, So now, because this is not, this is a user-defined one, I'm going to add the search package. And now I can simply get instance. Now I can say right triangle because that matches the name right triangle variate. Again, variate is optional. And here I'm going to say, give it 3.5. And then here, just to make sure that because I've written this, that means that all kinds of stuff can go wrong. So I'm just going to do a print line just to make sure that I've got the right value. And let's see how many. Let's generate 1 million of these things, and I'm going to put it into a text file. Just why? Because we're going to. Okay, so here we got the right triangle, 3.5. It's churning away, and then hopefully it has produced a bunch of numbers, okay? Now, do these numbers look like a right triangle? That's a good question. So let's use, remember I've mentioned this, this package called R. This is something if they're not teaching it to you in the stats class, it's something you should try to pick it up because it's quite powerful. So just let's read in the data. It has a method read table. And we just need to give it just point to and then I called it write t.txt. Did I spell it right? Yeah, hopefully. And then if I want to do it, now this reads into something called a data frame, which is something that R deals with. But, and so I'll just pick off the first column of that. Let's do 50 cells. And then we can either do it in the absolute or the frequency. And let's just do the frequency. Okay, that is pretty tiny, but there is what it produced. And that looks pretty straight to me. Okay, so the point being that even though that there was that square root thing, and the math said it should be straight, when we do a histogram, it looks pretty straight. Now, we could do statistical tests to see whether or not this is indeed straight. We could do a goodness of fit test to see whether or not this is indeed what it is, but basically it is. Okay, well, let's see. Here we do the same thing for the exponential random variate. If you remember, again, exponential has one parameter, and we pull the same deal here. The one difference here is that the parameter for exponential I'm calling the mean, and that needs to be strictly positive. Otherwise, if it's 0, you're just going to get a bunch of zeros. If it's negative, you're just going to get some weirdness. Although it actually would work with a negative. It just you would produce negative. A negative exponential. So that's, but nevertheless, the inverse transform method for exponential is minus the mean times the log of 1 minus our uniform, and the uniform we get with the draw. Nobody's questioned that minus. What do you think about that minus? Does that suggest that you might produce? Is it possible that this is going to produce negative values, assuming the mean is positive? And if so, why? If not, why not?
If the draw function only returns values between 0 and 1, that number inside the parentheses is only only at least going to be 0.
True. But what is the property of the log? Well, actually, the 1 minus is actually we could remove the 1 minus, but.
Well, the number inside the parentheses is always going to be between 0 and 1, and I'm assuming log is a natural logarithm in this case.
Yeah.
It's going to be a negative number because it's less than e. And so you need to have the negative on the mean and make it a positive number. So it's always going to generate a positive number as long as the draw function is between 0 and 1.
Correct, yeah. In other words, the log of any number between 0 and 1 is going to be negative. And so the negative is going to do the negative. And we would do that in pretty much the same way. So again, we're in a new virtual machine here, so we need to add the search package. And we can, now, because there's already an exponential in SimKit, the question is, if we generate from this, are we getting the one from SimKit, or are we getting the one that we just wrote here? And so to do that, we can simply print out which class we got. So when we run this, we see that the class that we actually got is the one that we wrote, the one in MV3302, not the one in SimKit. Why? Because if the user adds a search package, then it checks that first. And so that, the advantage of that is if you don't like the way that the built-in random variate works, if you think you have a better one, then you can use that better one. And so we can let's see, this was, I think, called it Exponential. And it's weird, it gives me these tiny little things. Okay, so basically that looks pretty exponential. Remember this right wedge thing that we did? Okay, so that again, it sort of looked like a triangle, but again, here we have two parameters that we need. And so we need to make sure that we give you exactly two parameters. And if they're not both numbers, then we're going to say, hey, we need numbers. And then here there's an extra little check here, because if as it turns out, if the product of these two is less than or equal to 1, then it has to be less than or equal to 1, just because of the way that worked out. But this was the composition method. Okay, so we said that if we had to generate two random variables. So one I called choice. If it was less than the product of the two, then we returned a uniform between 0 and that max value. Otherwise, we returned a triangle a right triangle with the same max value. And intuitively, there isn't much intuition here. In other words, if I were to show you this and say, what do you think this is going to look like if I generate a bunch of these, then unless your intuition is much better than mine, you're not going to, what the heck is that going to look like? But if you go back through the derivation, then, or if you kind of review your probability notes and then unravel this rule, you can actually figure out what the distribution is. Or, alternatively, we can just generate a bunch of them. So in this case, I've chosen a max value of 1.3 and a height of 0.6. And if we generate a bunch of these, and let's pull it in here, I think. Oops, where did you go? There we are. Okay, so, and actually what you can see, if you look, where they made this so tiny. You see that? you can't see that. That's a 6. That's a 0.6, I mean. So if you remember, there was a 0.6, a max value of 3.5, 1.3, I mean, and that's what has been produced here. In other words, if you remember, we started by drawing this picture, we derived that particular way of doing things, and then this is what gets produced. And then let's see, what else do we? Oh yeah, so now our second application of the composition method was for the full up triangle. And for the full triangle, not just the right one, the way that it's typically parameterized is we have a maximum value, a minimum value, and the mode. If you remember, the mode is the place where it's at its maximum value. So there, again, now we need 3 parameters. They all need to be numbers, and then we're gonna set them. And then again, overriding the toString. So the generate again this is in the composition method, you always need at least 2 random variables, whereas the inverse transform method only requires 1. So first we kind of pick our choice, which is going to be this uniform 0, 1. And then if you remember, if the ratio of the mode minus the min over the max minus the min, that was the probability that we will choose the one on the right. And then there to basically take the right, here we're taking the right triangle, we're stretching it out to the max minus min, and then we're shifting it over by the min. For the left triangle though, we look at the maximum value minus the mode, but then we kind of look at, we take the negative of that, and that flips the triangle over, and then we subtract that from the max. So, and again, if we are, once we've done that, we just need to get it from the random variate factory. And now there are actually 2 ways of parameterizing it. The one which is most common is actually the one that's least intuitive for a variety of reasons. I wish they'd done it another way, but this is the common way. The order of the parameters is minimum, maximum, and then mode. So it's like left, right, and center. The more logical one would be left, center, and then right. And if one is a little bit more general, then one could instead, I mean, here it's like if you do it the wrong way, you're just going to get something weird. A better way would be to actually take the 3 values and sort them. That would be a little more general, a little more user-friendly, but again, this is just for the classroom purposes. So we'll generate a bunch of again, the composition method. Again, if you just kind of look at this on the face of it, it's hard to believe that really is going to do anything. Again, we have these square roots going on, and we're just kind of picking one or the other, and is this really going to look like a triangle? So let's see. Where'd you go? Okay, so that looks like a triangle to me. And, for some reason this is, there are options I could give it to have a better sort of thing. But the minimum value was what? The minimum value was 1.3, the maximum was 4, and that's indeed what you have, and then you have it kind of looking like that. Again, just as a check, if we could make the, let's say if we made the mode a little closer to the maximum, and then ran it again, then we see that the mode gets shifted over. In fact, if we can even shift the mode all the way over to the right, and we're just going to get another right triangle. And let's see, just the final little piece is this, and this is in addition to the 3 generic methods, of which we've presented 2, there are a host of special methods, and this is an example of one of them. As it turns out, if I take 2 random numbers and take the maximum of them, then that will give me, well, what do you think that will give me? You can sort of guess by the name. That will actually give me a right triangle as well. And I can see you don't believe me. Okay, so yeah, well, so there it is. So what I did was I extended my what I had, just because I was lazy and I didn't want to rewrite the parameter stuff. Same parameters as our right triangle, but now it's this. I'm just taking the maximum of 2 random numbers. What could be the benefit of that? Well, that's probably a bit faster than taking the square root. Taking the square root can be an expensive operation. Taking the maximum is a less expensive one. So this could save some time, maybe. And then, okay, so same deal, only now I call it right triangle 2. And what did I call that? Right T2. And we see that does produce our right triangle. So the point is, well, there are 2 things. One is that the user-defined random variates are basically first-class citizens here. In other words, if I wanted to now, let's look at our arrival process. And use, let's say, let's use my right triangle. We can change this to so when I wrote the arrival process, of course we had no this didn't even exist, but now we should be able to use it. And we see that its inter-arrival time generator is the right triangle, and we didn't have to modify our arrival process in any way. So in other words, as long as we can kind of point the random variate factory to the right package, then the classes that we write will be first-class citizens. In other words, don't have to do anything special. Okay, so what that means is that if a particular distribution that you're interested in using does not happen to be in there, then you're not SOL. You can simply implement it and then point the random variate factory to the right package and then use that to your heart's content. So that's how to integrate new and different random variables into the simulation. Why bother with this? And why care? Because there are so many probability distributions out there that there is not a single package that I'm aware of that has every single one that's in there that exists. There are just too many. There are a bunch of standard, usual suspects. You know, your normal, your gammas, your beta, uniform, etc. But if you want to be complete in terms of having every single random probability distribution in there, then good luck. There isn't one that I know of, and no, but they don't even try. A lot of the commercial packages, what they will typically let you have these sort of clunky things where it's like if I want a distribution that's not in there, then I have to kind of approximate it with a piecewise linear thing, and then they'll let you kind of do something kind of clunky like that. But they will typically not let you use an entirely new one. Anyway, so that's really all I have for today.